Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 12, Solids. So in this section, we're going to be talking about solids, and in the next two sections, liquids and gases. But we're not going to focus on the chemistry issues. We're going to be focusing on the physical issues, that is, the issues related to physics. We'll talk briefly about the crystal structure of solids, just to give you a background. That's a little more chemical, but then we'll move to more physical aspects of it. So after the crystal structure, we'll talk about density. Density can be applied to any substance, whether it's solid, liquid, gas, or even plasma. But we're going to focus on solids right now, and to a lesser extent about water. We'll talk about the concept of elasticity, and it might not be what you think it is, because we don't use the word the same way in physics as we do in everyday English. We'll talk about stresses, the two versions of stresses: tension, which is the pulling away, and compression, which is the pushing into. We'll talk about arches, which take advantage of compression forces to give strength to the arches. And then we'll talk about a concept called scaling. Scaling refers to the ratio of the surface area of an object to its volume. And that becomes very important because surface area is directly related to strength of an object. It could be strength of an animal's leg, it could be strength of a building, versus its volume, which is related to its weight or mass. So we'll talk about that. So crystal structure. So atoms in a solid tend to be arranged in one of two very general ways. And the first of those is in what we call a regular array or a crystal lattice. That is, it forms a crystal. And solids that you're familiar with that would be in a crystal format, in other words, a very regular pattern of atoms lined up, would be minerals, ice, which is actually technically considered a mineral, salts, and when I say salts, I don't just mean table salt, sodium chloride. To chemists and physicists, salts means any ionic compound. In other words, any compound composed of positively charged ions and negatively charged ions, and these tend to form very regular lattices, crystal structures. And metals. Metals, they're not ions, they're individual atoms, but they're packed together with very strong bonds between them, and they are considered to be in a lattice structure. And if you look at these top two pictures here, the one on the right shows just a microscope view of sodium chloride, table salt. And you can see it forms very nice little cubic structures, and that's actually called the cubic crystal form. And the reason for that, in part, is because of the way the individual atoms pack together. If you look at the diagram on the left, you see chloride ions that are shown in green. This is a drawing. And sodium ions shown in kind of reddish brown. And you'll notice that they alternate in the packing. And in fact, every chlorine is surrounded on all sides by a sodium, except on the edges. And every sodium is surrounded on all sides by a chlorine. And since they're ions, we call them sodium ion and chloride ion. That's the difference in names. So this forms a very tight lattice structure. In this particular structure, the atoms are in a 1-to-1 relationship, a 1-to-1 ratio. There are other ionic compounds that are not 1-to-1. They might be 1-to-2, 2-to-5, 3-to-7, all kinds of versions of this, but sodium chloride is pretty straightforward and simple. And so you have this very regular lattice form in a lot of crystal structures. And one way that people took advantage of this very regular repeating pattern in the structure is by trying to analyze it with X-rays. And it turns out that if you bombard crystals with X-rays, X-ray beams, X-rays have very, very small wavelengths. And depending on which wavelength you choose, those wavelengths can actually match the size of the atoms, or the energy, the frequencies can match the energies of the bonds between the atoms. And by doing this, this middle diagram here in black and white with the little green rays, that represents an X-ray diffraction machine or an X-ray crystallography instrument. And what happens is you have a cathode or some other device that generates X-rays. X-ray in the EM spectrum, the electromagnetic spectrum, and it shoots out rays, and you have a little slit where only a thin beam can go through. That's what's showing here in the black. That's showing the slit that allows one beam to go through, and it hits a little crystal. That's what the little rectangular box in blue is. And when it hits that crystal, it will interact with the atoms because the wavelength of the X-ray matches closely to the wavelength of these structures, or it's smaller or roughly around the size, and you'll get a lot of interactions. You'll get scattering of the X-rays and the various particles that are released from the crystal. They might be electrons, they might be bigger pieces coming off, and then you have some detection device, this curved thing at the bottom here, that detects all the different fragments as they hit at different angles. And then you use a very, very sophisticated computer system to kind of back calculate what the structure of the crystal might be. Think of the difficulty of this technology and the advancement of this technology as if you went into an empty room and shot an apple with a big gun, and it blew up and all the pieces of the apple scattered all over the walls. And then you let somebody else come in the room and look at the walls, and you said, okay, what did I have in the room before I blew it up? And that's kind of what X-ray crystallography is. You're looking at a pattern, and then you're deconvoluting what the original structure must have been like to give that pattern. Now, there are also other kinds of solids that are not in regular patterns. We call these amorphous solids. Amorphous comes from two Greek words. A means not or without, and morphous means shape. So this literally means doesn't have any real shape, doesn't have any real pattern to it. Glass is the most classic example of this. If you look at quartz crystals, they're silicon dioxide crystals, and the silicon dioxide is repeating in very, very specific patterns. But when you melt down quartz in the form of sand, you grind it up if it's not already ground up, but sand is essentially little pieces of quartz, most of it is, and you grind it up and then you melt it, you lose all that structure, and then you let it cool relatively quickly. Well, it doesn't have time to form crystals, and you get this mishmash of bonds being formed and holes and no regular pattern. And that is what glasses are. Not just the glass we're familiar with in window panes, but you can have volcanic glasses like obsidian. You can have other amorphous solids like rubber or wax or tar. A lot of polymers are not regularly patterned, so plastics may be in this category. And there are even some metallic glasses where they've been heated up to lose the pattern and then cooled quickly, and you get the solid reforming, but not in the same crystalline pattern. And I forgot to mention in the bottom here, that pattern is the pattern from sodium chloride that you would get from bombarding a crystal of this regular chloride, sodium pattern in the crystal. All right, so crystal structures, as well as any solid structure, they involve a lot of different kinds of bonds. And the three main categories of bonds, there's another one that's sort of a subset of covalent. I won't get into it. You have ionic, covalent, and metallic. And ionic is when you have bonds between atoms that are full ions, a negatively charged ion like chloride and a positively charged ion like sodium, and they attract each other strongly. And in fact, that positive ion attracts a lot of negative ions all around it, and the negative ion attracts a lot of positive ions around it. And you end up with that lattice I just showed you in green and red of sodium chloride. That's a typical ionic compound. Covalent compounds are a little different. They don't have full-blown charges. One atom may be slightly more negatively charged than another, and the other might be slightly more positively charged than the other, but they don't have to be at all, and they just share electrons instead of one being fully negative with all the electrons and one being fully positive, missing its electrons, and then being attracted by electrostatic forces. You have bonds that are actually shared. They share electrons in order to bring them together. That's a covalent bond. And then metallic bonds, this is a sort of a little mixture of each. It's probably more covalent. The metals will form bonds together, but the electrons are not directly shared. They kind of donate an electron to this cloud that essentially swims all around the metal throughout the metal crystal. And we call it a sea of electrons. You'll hear people call it a sea of electrons or an ocean of electrons. And that those electrons, because they're all over the place between all the atoms and they're moving sometimes, especially if current is going through them, they provide a very, very strong linkages between each of the metal atoms in a chunk of metal. We're not going to go into detail about these. I just want you to see these are the three that are considered full bonds that attach atom to atom within molecules or within crystals or within ionic compounds or within metals. We also have a fourth kind of bond, and this is actually a collection of different bonds that are all weak bonds between whole molecules. So you don't see these so much between ionic and metallic. You see them with covalent compounds where here's a covalent compound and here's a covalent compound, and they have a weak attraction towards each other, and there are various types of these weak attractions. They're all put under the catchphrase of van der Waals forces or van der Waals bonds, named after a very famous scientist named van der Waals. So the properties of any solid are dependent on a couple things. Which bonds are being used to keep the atoms together and which atoms are being kept together. And that will really determine the properties of that particular solid. Now, obviously, this is not a chemistry class, so if you want more information, I'm happy to give it to you. I teach a lot of chemistry courses. I've taught several at Del Tech, but we're going to focus more on the physical aspects from here on. Okay, so density. This is a physical characteristic of solids. It's also a physical characteristic of liquids, gases, and even plasmas. It is the amount of mass per unit volume. In other words, take the amount of mass, divide it by the amount of volume, and you get the density. And this can be thought of as how much stuff do I have crammed in a certain amount of space. So if I have 1 centimeter cubed, a cubic centimeter, so I'm taking a centimeter, which is like less than half an inch, and I make a box. All sides are a centimeter. That's a cubic centimeter. And that box, cubic centimeter, also called a cc, also called a milliliter. These are all equivalent. And if you ask how many grams are in that space, that would be the number of grams per milliliter, or grams per cc, or grams per cubic centimeter. Those are all the same unit. So here are some of the units, and the ones I just talked about are on the right. The first three in that group on the right: grams per centimeter cubed, grams per cc, which just stands for centimeter cubed, grams per milliliter, and that is because a centimeter cube is a thousandth of a liter. A liter is a box about the size of a cigarette by a cigarette by a cigarette. That's a liter box, and if you divide that in 1,000, you will get a cc, or a milliliter. Milliliter literally means thousandth of a liter. The last unit on the right here, kilogram per liter. Totally different unit, but it's actually equal to each of those three. So if you look at the third one, grams over milliliters, if you multiply grams by 1,000, you get a kilogram. If you multiply milliliters times 1,000, you get a whole liter. So that last unit is just what you would get if you multiplied the top and the bottom both by 1,000. You would get kilograms per liter. So it's exactly the same unit. It just has very different pieces to make that unit. Now the unit on the far left here, kilograms per meter cubed, this is the unit that is favored by physicists. The one on the right is favored by chemists, usually in tables that they provide. So in this class, we'll tend to use the SI unit, the kilograms per meter cubed. It's the SI unit because the standard international unit for mass is kilogram, and the unit for distance or length is meter, and a volume is a length unit cubed, because a cube would be a volume. So this is kilograms per meter cubed. And this unit is actually, when you work out how it changes, it's 1,000 times smaller than all the other units on the right. And what that means is, if you see a number associated with it, its number has to be 1,000 times bigger than the units on the right in that group of 4. Now here's an example. So the density of water is 1 gram per centimeter cubed, 1 gram per milliliter, 1 gram per cc. Very close to 1 gram. And the reason for that is because originally, 300 years ago, when the gram was first defined, it's since been redefined. When the gram was first defined, it was defined as the mass of water that will fit in a cubic centimeter box. So the density of water is by definition 1. Now, if you actually look up tables, it changes depending on the temperature, but when it's about 4 degrees centigrade, it's pretty close to 1 gram per centimeter cube, and we'll just use 1 as the number for any temperature in this class, unless you hear otherwise. But 1 gram per centimeter cubed, or 1 gram per cc, or 1 gram per mil, is the same thing as 1,000 kilograms per meter cubed. And that's because kilogram per meter cubed is 1,000 times smaller unit than grams per centimeter cubed. And therefore, you need 1,000 times bigger number. So the two values are exactly the same. It's just you're accounting for the different units. So weight density is very similar to the regular density, which is really a mass density. It's mass per volume for the regular density. It's weight per volume for the weight density. So instead of using units of mass in the numerator, you use units of weight, and that could be either newtons or pounds if you're in the imperial system. So in the metric system or the SI system, you would use newtons per cubic meter. Whereas in the imperial system, you would use the old unit of pounds per cubic foot, or foot cubed. And if you want to convert a mass density, a regular density, to a weight density, you just multiply the regular density with the mass per volume units times 9.8 meters per second squared. Remember, that's gravity. Remember, if you multiply mass times gravity, g, you get weight. Well, we're just multiplying mass density times gravity to get weight density. The only difference is we're dividing both sides by a volume, which is meter cubed. So there's nothing special with that new formula. All right, so density depends on two major things. How heavy all the individual atoms are, how much mass they have. If you hear me say heavy, I generally really mean how much mass they have. On Earth, that's similar because we have gravity, but if you're in outer space, we won't talk so much about weight as we talk about mass. All right, so density depends on the mass of the individual atoms that are packed, and then how close you pack them together, the spacing between them. And there are limits for how much you can pack them together, but if you have solids, they tend to be pretty well packed. Liquids, they tend to be moving a little bit, but fairly well packed. And then gases, they're all separate, and they're all flying around, and they're completely unpacked. And that would have the lowest density, of course. So density is a property of matter. It's what we call an intensive property of matter. I'm not going to quiz you on that. Intensive just means it's a property of matter that doesn't matter how much matter you have. So if you had a small amount of matter or a large amount of matter, it will have the same density if it's the same substance. So the density of 1 nanogram, that's a billionth of a gram, will be the exact same density if you had 5,000 kilograms of it, a pile of gold. The density is the same. Why? Because while you're increasing the mass, you're increasing the volume by exactly the same fold amount. You're multiplying both by the same amount. And therefore the ratio, mass to volume, which is what we call density, stays the same. You bump one up, you bump the other up, they go together, and density is still constant. And that goes for whether we look at two different masses, whether we look at two different weights, or even if we look at two different volumes. If I have a flake of gold, tiny little piece that a prospector might find in a river, and of pure gold, and compare that to a big gold brick, they have identical mass, the same amount of mass packed per volume. One has a little bit of mass and a little bit of volume, one has a lot of mass and a lot of volume, but the ratio is the same. And in the case of gold, that ratio is 19.3 grams per cubic centimeter. I'm not going to quiz you on that. I'd give you that value if necessary, but that equates to 19,000. Remember, we have to bump it up by 1,000 for the other unit, 19,000 kilograms per meter cubed. So a chemist would report the first number, and a physicist might report the second number. But something I want to point out here, these numbers, you'll notice, are 19 times bigger than the two numbers I showed you for water, 19.3 times bigger. What that means is gold is 19.3 times denser than water. What does that mean? Well, that means if I have this much water, it would weigh about 19 kilograms. I'm sorry, it would weigh, let's say I had 1 liter of water. I'm sorry, that would weigh 1 kilogram. 1 kilogram. But if I had this much gold, it would weigh 19.3 kilograms, 19 times as much mass. I say weight, but I mean mass, okay? And I point this out because next time you watch a movie that involves somebody stealing a lot of gold, watch the actors carrying the gold bars. Those gold bars, typical gold bars that are made in the US and most countries, weigh about 27.5 pounds. You'll see them carrying bags of these things over their shoulders like it's nothing. You would never be able to carry that much gold. In fact, you'll also see occasionally where they'll replace gold with lead and paint it with gold paint and hope that nobody notices. Gold actually has a density of a little above 11. So this is almost twice as dense. So if you had a lead bar and a gold bar, and they were both colored gold, you painted the lead bar gold, you would know which one was gold instantly when you pick them up. The gold bar will weigh almost twice as much as the lead bar. So just a little trivia for you next time you watch a movie that involves stealing gold. All right, elasticity. Now, we're going to talk about the physicist's definition of elasticity, not the everyday use of elasticity. Usually we think about elasticity, oh, it's very stretchy, it's elastic. Rubber bands, those are elastic. Suspenders, those are elastic. A rubber ball, that's elastic. But the physicist has a different way of looking at it. So an object subjected to any external forces, so something squeezing it, something stretching it, can change the shape if you give it enough force. I think that's pretty obvious. The elasticity refers to how much that object, that material, resists the change in shape when the deforming force is applied, and it also refers to how well it springs back to its original shape when you take away the external force, when the external force is removed. So things you usually think about as being very elastic are not really that elastic by this definition. Things that physicists would consider elastic are springs, especially very tight springs that will be hard to move, but once you move them, boom, they spring right back into place. That's an elastic spring with high elasticity. That's the noun we would use. Most sports balls have a certain amount of elasticity. Golf balls, baseballs, we think of those as solid objects. But if you ever look at photographs of just when that ball is hit, when a golf ball is hit by a club or a baseball is hit by a bat, you will see major deformation of the shape of that ball. The ball will be flattened, something fierce, as the force comes in from the bat or the club, and the ball will be compressed on a side as it's being hit. But it resists that hit, but it does have to give because you're hitting it with so much force. But what makes it elastic is the fact that as soon as you hit it and the ball flies from the bat or your club, the ball immediately springs back to its original shape. So that would be considered high elasticity. We make struts for cars. I don't, but people make struts for cars that are essentially incredibly stiff metal springs. And these springs will give under the force of the car moving or the car bumping around, but they are extremely stiff and they will bring the car back to its original position because the spring itself wants to restore its shape immediately. So that we use very high elasticity metal springs in struts. The same thing with construction beams. They're not springs, but they are made of steel, and these steel beams can give a little, not too much. They resist a lot of force, but when they are bent or deformed, the second the force comes off, they straighten right back up again. And the same thing with bridge bearings. These are the supports underneath bridges where the bridges are basically attached to the ground. These things will give a little bit, not too much, but enough to kind of soften the road and protect the bridge from any damage and protect everybody on the bridge. So a substance is more elastic if it has more resistance to the deforming force. In other words, it's hard to deform it. And two, if it returns to shape more quickly after the force is removed. So what that means is if something is very elastic, it means it's hard to change its shape. But if it does change its shape, it's quick to spring back to its original shape. That's what elastic is, or elasticity is to a physicist. So materials that don't return to their original shape are what we call inelastic, low elasticity. So these would include things you might be familiar with: clay, Play-Doh, putty, many plastics. If you deform them, they don't come back. Glass is considered inelastic, not so much that it doesn't spring back, but it'll shatter and it's not very resistant to force. Most glasses aren't. Lead's a soft metal. Gold's a soft metal. Copper is a soft metal. All of those, if you bend them, if you took a copper wire and bent it, it's not going to spring back. You'll see it'll just stay there. If you had a piece of lead and you were able to bend it or hit it with a hammer, you can flatten it very easily, and it's not going to spring back. But steel, that's going to spring back. Reinforced alloys, strong alloys, metal alloys. Alloys are mixtures of metals, usually mixed for some purpose. So bronze, brass, steel, these are all alloys of metals. They're a mix of metal and either other metals or metals and other substances. So with enough force, all materials can be deformed. I mean, if you take a steel ball and put it under a heavy press with millions of pounds of pressure, it's going to deform and it's not going to come back. Eventually, you'll overextend the elasticity of almost any object. So it's not that it's forever with its elasticity. It's not an infinite elasticity. It has to give eventually. All right, so what's more elastic? I think you probably already know this from what we talked about. Steel, rubber, they're equally elastic, not enough information. Well, I think clearly from our discussion, steel is the more elastic by a physicist's definition. It's more resistant to change, and it's quicker to reform its shape. We think of rubber as being very fast to reform its shape, but steel is even faster. Steel really does not want to be deformed at all. And so it'll return to its shape immediately. It resists force much better than a lot of materials. Titanium is another thing that really resists force on it, and they will retain their original shape and return to their original shape much faster and quicker than things like rubber or plastics would. So don't confuse how stretchy or how flexible something is with the elasticity as a physicist uses the term, okay? Flexibility and stretchiness, that's the way you usually think of elastic, but physicists, it's a very different definition. And this leads us to something called Hooke's law. Hooke realized that if you took a spring and you put a weight on the spring or you pulled a force on the spring, so it could either be a horizontal spring and you're pulling a force on it, or a vertical spring and you're putting a weight on it, which is a force. Remember, weight is a form of force. It's just the force due to gravity for that mass. It'll pull the spring. It'll extend the spring. And if you push the spring with a certain force, you can squeeze the spring together if it wasn't already packed together tight. So the amount that you stretch a spring or the amount that you compress it relative to what its resting state is. A spring might be resting and have some space between it and be very stiff, like the strut of a car. And you'd have to put a lot of force on it to squeeze it, and you'd have to put a lot of force on it outwards to extend it. So that change in distance, whether it's squeezing it smaller or stretching it bigger, that change in distance, the delta x, the change in length, is directly proportional to how much force you put on that spring. And because it's directly proportional, we can just throw in a constant to turn that proportionality into an equality. So we just throw in a constant. They call it Hooke's constant for obvious reasons. So the equation would be force equals some constant, and every spring has its own constant. Really stiff springs have a high constant, and really weak springs, very light springs, have a very small constant, very small Hooke's constant. But they both have this direct proportionality relationship. You increase the distance, you require more force. You put more force, you get more change in distance. Either one will change the other in the same way. I double the force, I'll double how much I stretch it. I triple the force, I will triple how much I stretch it. If I stretch it 3 times as much, I need 3 times as much force. If I compress it 3 times as much, I need 3 times as much force. So, a 10 centimeter long spring, so the whole spring, the resting spring is 10 centimeters, extends to 12 centimeters when a 1 kilogram load, so you'll notice we're talking about mass instead of force, We'll talk about that in a second. A 1 kilogram load is suspended from it. What would be its length if a 3 kilogram load were suspended from it? 14, 16, 20, or 24 centimeters. Well, let's think about this for just a second. Look at the little springing spring here. You've got a weight sitting on top of it. We know that the amount of stretch, not the full length, the change in the length, how much it's stretched, not what it's stretched to, it's the difference from what it stretched to minus what it used to be. That difference in length is directly proportional to the force. Well, we know that the force is directly proportional to mass because we're on Earth and we have gravity. So if we know that the change in the length of the spring is directly proportional to force, and we know that force is weight, it's weight in this case, we know that's directly proportional to mass. Remember, it's mass times gravity. Well, then the change in the distance must also be proportional to mass. So it doesn't matter whether we use mass or force units, whether we use kilograms or newtons that we're pulling a spring down with or stretching a string horizontally. It does horizontally we have to use a different formula. We can't really use mass in that case because it's not gravity horizontal. But if vertical, it can be force or weight. It doesn't matter. It's still the same proportional relationship with how much you change the length. Now look at this problem. We used to have a 10 centimeter spring. It was extended to 12 centimeters. That means we increased the spring by 2 centimeters, not 12, 2. 2 is the length that was increased by a 1 kilogram load. If we have 3 kilograms, we're going to triple. We've tripled the load. We will triple the extension length. So instead of 3 centimeters, we will extend it 6. But remember, the original spring was 10 centimeters. So we add that to the 10, and we get the answer 16 centimeters. So you have to be a little clever about this. You have to remember, okay, that's not they didn't tell me how much it actually extended. I have to read the problem carefully to see how much it stretched or compressed. It'll be the same answer, okay? And then compare the difference in the loads, whether they're both kilograms or both newtons. It's not really that important for this kind of problem. All right. So when something's stretched, when something's pulled, we call it tension. We call it under tension. That is a stretching of something. And we've talked about this with tension forces and wires and cables and ropes, etc., string. That happens all the time. You see tension whenever anything is pulling on it, when two things are hanging from a rope that's over a pulley or whatever. You get tension in the string. You can get tension not just in very flexible things. You can get tension in very solid things, like steel beams in a building, or tree limbs, or rocks, okay, that are put under tension because of pulling forces on either side. When things are squashed together, it's just the opposite. We call that kind of force compression forces. So you have compression forces squeezing together, and you have tension forces pulling apart. And here's an example where you'd find tension forces and compression forces. So if you have a girder that's under stress, and this is a version where the girder this is a steel beam that's sticking out from some structure, and it's got its own weight hanging off the structure. In this picture, we're showing an additional weight, but we didn't have to show an additional weight. The beam itself has its own mass, its own weight. Think about where the center of gravity is on that. In the center of that's pulling it down. It's pulling it down, and it's pulling stress on it. And that stress will end up bending the beam. You might not see it, but there's a little microscopic amount of bending in some cases, and it's stretching the top surface because of the way it's bending. And the bottom surface is being compressed. So if you can even do this with your finger. If you just take your finger straight and you bend it at one knuckle, you can see the top of your knuckle is stretched out. And the bottom of your knuckle is kind of, all the skin and muscle are kind of squished together. That's your compression, that's your tension. So you don't need any aid. You can just look at your finger and go, oh yeah. If I have an object where the stress is at the ends, if the weight is at the end pointing down, I will put tension on the top and I will put compression on the bottom. Now, what's interesting about this is if you have a lot of tension on the top and a lot of compression on the bottom, if you go through the thickness of this material, the tension is going to get less and less, and eventually you're going to start getting more and more compression, which is in the opposite direction. Well, what that means is in the middle, there has to be some point where the amount of tension is exactly equal to the little amount of compression, and therefore there's actually no stress in the center line of that object. And we call that the line of zero stress. And that's the part where there aren't any forces stretching or compressing in the length of that beam or tree limb or whatever structure you've got. Now compare this to another situation where you have two supports on the object, and now where is the center of gravity? It's in the center, and I show a weight on the top, but I didn't have to. The center of gravity is still in the middle of this beam that's supported on two ends. So it's weighed down in the middle, and now what happens? Now you've got the tension on the bottom is being stretched, and the top is being squeezed together. And if you want to convince yourself, I got a little stick here, so I'll just take a stick and you've got forces of support on the left and the right, so I'll just do it like I'm pushing up on those forces. Well, if I push up on those forces, it happens so quick you can't really see it. Let's see if I can get another stick here. But what you should see is the bottom being split. There we go. Bottom being split. Let's get that right. The bottom being split because it was torn apart by the tension forces, but the top has compression forces, and that's what kept the top of this together. Now, if you wiggle it back and forth, now you switch the tension forces to the other side, and it breaks. And people do this all the time with sticks, don't realize that's what they're actually doing. They're putting a tension force on one side, then they're putting a tension force on the other side, depending on how they force the material. So I-beams are used in construction very commonly. And you might have wondered, why is it shaped like this? Well, it turns out the reason why it's shaped like this is because of tension and compression forces. If we had an absolute solid beam of metal, in other words, it was rectangular, cross-section rectangular, instead of this I-beam where the cross-section looks like a capital letter I, that's why it's called an I-beam. If we had this big, heavy, rectangular-shaped beam that was solid all the way through with no indentations in it, that's a lot of mass in the middle. But when you put this beam in, and if it's layered like this with the wide part on the top and the wide part on the bottom, remember, no matter whether it's sticking out of a building when the tension forces are pushing on the top and compression on the bottom, or it's being supported by two different supports, think of my elbows as supports, and it's being weighed down in the middle, and now the tension forces are down here and the compression forces are up here, it doesn't matter. The beam is thickest at the part that has all the stresses on it. So it's wide at the top of the eye, it's wide at the bottom of the eye. No matter how you're using the beam, as long as you orient it this way, you don't want to turn it sideways. That defeats the purpose of the beam. You keep it like this, and now the tension forces, if they're on the top, and the compression forces on the bottom, they're two thick parts of the beam there. And if you have a different structure where it's switched, it's still the compression forces are on the top and the tension forces on the bottom. It's still wide on there. You don't need all that extra metal. It just provides extra weight without that much extra strength. The middle part of the eye is just there to connect the two strong parts of the beam together. So this is a really efficient use of steel without using too much steel to get a maximum amount of strength where you need strength for tension and compression in a structure. So it maximizes the strength on the top and the bottom, whether the tension's on the top or the tension's on the bottom, and vice versa for the compression. And it minimizes the weight in the middle. So think of it as if the weight was just scooped out of the part on the sides that you didn't need it for. It just has extra weight that has to be supported by the rest of the building underneath it. So you don't want that. And it also is more expense to have more metal. So here's a question that uses these concepts. Suppose you drill a hole horizontally, so we're cutting it right through a tree branch, as shown. Which hole will weaken the branch the least? The top one, the one near the top, the one near the middle, the one near the bottom, or it doesn't matter? Well, think about this. This is a tree branch. It's sagging from its own weight. It's hanging down, which means the forces are pulling the end down, and you're going to get tension on the top. You'll also get compression on the bottom. Remember, it's like your finger. Think of the weight on your finger. Here's the end of the tree branch. It's pulling down, stretched on the top, it's compressed on the bottom. Those are the places where you need wood to support the tree branch the most. You want the wood in the top for the tension. You want the wood on the bottom for the compression. Otherwise, it might break. The wood in the middle is not nearly as important. By drilling one hole in the center, you're probably not going to change the strength of that tree branch that much, and therefore you would carve it in the middle. So another structure that takes advantage of these compression and tension forces, especially the compression forces, are arches. And before the days of arches, people had more or less flat roofs on all the structures, and they required a lot of supports at different points. And this is a picture of the Parthenon in Athens, Greece. The ancient Greeks barely used arches at all. They weren't really common at all. The arches were invented probably in Mesopotamia, with present-day Iraq and surrounding areas, Iran, Egypt, possibly Syria, but they didn't get to Greece too much. So Greece used these long roofs with lots of columns that were necessary to hold up this roof structure because it was so heavy. It's made of stone. But arches were invented by Middle Easterners and Near East people. They were also used in ancient Mexico, in ancient China, and ancient India, but not very much. Nobody used them that much until the Romans. The Romans learned it from the people that lived in Italy before the Romans, which were called the Etruscans, and they just went wild with arches, and they loved arches, and they became masters at the architecture of arches. And arches really take advantage of these compression forces. In fact, what they do is, instead of making the compression force a disadvantage, they make it an advantage by shaping the structure in this arcing fashion, making the arch. That's why it's called an arch. It's an arc. Okay. The supporting columns that are on the side of the arch are all you need. You don't need all these extra giant columns shown in the top picture in a typical Greek temple. The arch will support a lot of weight if you build up a flat surface on the top of the arch. And it takes advantage of compression, because the more weight you push on it, it pushes along the curvature of the arch itself. And it's all compression forces. So you have the weight on top, and that is turned to, because of the angle of the arch itself, the forces are directed along the stones that form the arch and then eventually end up pointing down. And the more force you put on, the more you compact the arch better. So higher forces actually make the arch more stable due to this beautiful compression parallel along the lines of the arch itself, and therefore it just squeezes the rocks together, and the weight pushing together makes the arch even stronger. And so they use the ability to stone to increase the strength of the structure. Now, stones are terrible at withstanding tension forces, being ripped apart, but they are excellent at not being compressed. So that's why an arch is such a beautiful thing to make when stone is your main material for building. But arches can have different incarnations. That we can do different versions of arches. And if you have these almost natural arches. There's a natural arch referred to as a catenary. And a catenary is a shape that if you took a chain and you just held a chain with one hand and you held a chain with another, like the boy here is showing, and you just let it hang, that shape, mathematically, you don't have to know this, is called a hyperbolic parabola. Not a hyperbolic parabola, a hyperbolic cosine. A hyperbolic cosine. And this shape also is known as a catenary. And the reason why it's called a catenary is catenary comes from a Latin word, caterna, which just means chain. So literally, if you hold a chain, you'll make a catenary shape, a chain shape. And it turns out this shape has a lot of strength for supporting itself, either when it's hanging down low or when you turn it into an arc structure. And the famous arch of the St. Louis Arch in St. Louis, Missouri, this arch has that shape. It is a catenary shape. It is a hyperbolic cosine. And this arch, because of its shape, the tension forces actually hold it together. It makes it very hard to build. It doesn't have the strength or any of the strength of the structure until that last piece is put in. So whenever you're building any arches, like the stone arch I showed you before, you have to have some support until you put the last piece in, that top piece. That's called a keystone. Don't worry about that, but that's what it's called, the keystone. And once you have that in, the whole arch has a great deal of strength. And this arch was built in St. Louis, and it's very strong, and it has that catenary shape. Now, if you start putting weight on the shape, either an arc that's like the shape of the St. Louis arch or the chain that's hanging down like this, a slightly different curve is formed. Instead of that catenary mathematical formula, it's a slightly wider formula to support weight that's being pulled on the chain or weight that might be sitting on top, flat on top of the arch. It changes that shape. The best shape in that case is an actual parabola, which you might be familiar with from algebra classes. It's a little bit steeper than a catenary. I said a little bit flatter. It's a little bit steeper. It depends on the formula you use. All right, so the arc shape is when you throw a ball in the air. The parabola, if you ever want to see what a perfect parabola is, just throw a ball up in the air and watch the arc it forms. That's a parabola as long as there's not sufficient air resistance or wind that day. But the shape of supporting cables hanging on a suspension bridge, those are cables where you have the cable hanging like this, and all along the length of that hanging cable, there are ropes or cables holding up the bridge. That will change the shape. It changes the best shape from a catenary to a parabola. And so those are two places you will see parabolas in everyday life. Now, if you take one of these arches, if it's supported, you want the parabola. I mean, if it's supporting more weight than itself, you want the parabola. If it's not supporting any other weight except itself, it's just itself, then you want that catenary. But if you took that curve, so you made that curve here, and you just rotated it around in 3 dimensions here, just twisted it, you'll get a dome. Try to envision that, just a little curve here, and if I twist my fingers around, that shape that it will make is a dome. And that's where domes come from. They're 3-dimensional catenaries or 3-dimensional parabolas, depending on what you're using. I believe this one for the Jefferson Memorial, I believe that's a catenary shape. Okay, new topic, scaling. So scaling is also involves the shape and size of structures, but it involves comparing certain aspects of the structure. And when we're looking at scaling, we're looking at 2 major categories of aspects of a structure. We're looking at things that affect the volume of the structure and things that affect the area of the structure, the cross-sectional area or the surface area of the structure. Volume is a 3-dimensional mathematical formula. If you have the volume for a cube, it's the side cubed. If you have a volume for a circle, it's the radius cubed times a couple constants. We're not going to worry about the constants, 4/3 pi. But it's always based on a cube of some dimension, some linear dimension of that size of the object. Whereas area is always based on the square of some object. If I have a box, if I have a square, it's this side times this side. If they're the same size, it's this side squared. That's why we call it squared. When we're multiplying 2 things together, we call it a square because it's the area of a square. We call a cube because when you cube the numbers together, the sides together, you get the volume of the cube. I think one of those caused the name of the other. I forget which way it went. But that's why they're related names in each of those cases. But it turns out volume, because density is constant for a material, a big volume means a big mass. Big volume means a big weight. A little volume means a little mass. A little volume means a little weight. Those are directly proportional to each other. You have more volume, you have more weight, you have more mass. However, you don't have more strength. Strength is related to the area of an object, usually the cross-sectional area. So think of an elephant's leg. An elephant's leg, if you were able to saw through the elephant's leg, and I'm not suggesting you actually do this, and look to see how big that area is. It's probably about this big. or bigger actually, much bigger. The surface area of that cross-sectional area will give you an indication of how strong that leg is to support the animal's weight. But the weight is related to its volume, which is a cubic term. So area is based on a square of the dimension, how wide it is squared, whereas volume is based on how wide it is cubed. And those two numbers, if you increase them or decrease them, will change very differently. So strength is related to the area of the cross-section. That's a two-dimensional term. So it's related to whatever length dimension, width dimension you have squared. Whereas weight and mass are related to the volume, and that's a three-dimensional term. So that's related to the width or depth or height cubed. Well, if you're making something bigger or smaller, you're going to change if you made it bigger, the volume is going to change a lot faster than the area is going to change. And that means the weight is going to change a lot faster than the strength. And if you go down smaller, it's the weight will change dramatically and the area will change less. And the area will always change less than the weight. The weight will always be the bigger effect. If you're going down in size to something smaller, you end up with really good ratios of strength, which is the squared term, to the mass, which is the cube term. But if you're going up big, eventually you get to an object that's so big, like animals that are bigger than dinosaurs got. Eventually you'll get to a size where the strength of their bones can never be enough to support the mass of their volume. Okay, so the people that build structures and people that look at animal structures or people that look at buildings or something else they're constructing have to be concerned with this ratio of surface area, that's a measure of strength, to volume, that's a measure of weight or mass. And you want to make sure that when you increase the size of something from some scale model or some smaller version to some bigger version, that you have enough strength to cover the much, much bigger mass that grew a lot faster. So some objects will become so big that the strength of the object just can't keep up with the weight, because the weight is increasing by a cubic term, cube of the change in whatever you're doing, and the strength is increasing by the square of whatever you're doing. So let's look at an example with just plain cubes. If you have a cube on the left here, that's 1 by 1 by 1. We're not going to worry about the dimensions. It's in centimeters, and the mass is 1 gram, but let's just use unitless for most part. So the surface area of one side is 1 times 1. So that's 1. And the volume of this is 1 times 1 times 1. It's a cube. Well, that would give you an area of 1 divided by a volume of 1. That's a 1-to-1 ratio, so that's 1. Fine. But what happens when you double the length, the width? Because when you're doubling the width, you're not just doubling the width, you're doubling the height, you're doubling the depth. I don't know if you remember the Mike Myers movies, Austin Powers. Mini-Me was 1/8 the size of the evil character in there. I'm blanking out on his name. Dr. Evil. He's 1/8 the size. Well, that means they made his height half, they made his width half, they made his depth half. Half times half times half is 1/8. So that was a scaling thing. They scaled him down 1/2 in all dimensions. That's why he was a 1-to-8 ratio. In the case of doubling, you get the same kind of thing. The volume is now 2 by 2 by 2. 2 times 2 times 2 is 8. So instead of a volume of 1 that we had before, we have a volume of 8. We've increased it 8-fold by doubling the width. But the area of any one side, we increased only 4-fold. It's a 2 by 2. So the area went up 4-fold. The volume went up 8-fold. Well, the volume and the mass will both go up 8-fold. So the weight will go up 8-fold, but the strength will only go up 4-fold if we're thinking about the strength of the cube. And when you go up to 3 centimeters, now you're tripling it. We'll compare the 1 to the 3. We're increasing it by 3-fold. And you can see how this works. Each time you're increasing the surface area a lot, but you're increasing the volume even more. So the surface area to volume ratio is always going to get smaller and smaller every time you make something bigger. Well, how much smaller does it work out to be? Well, because the surface area is going up by the square, remember surface area is related to strength, and the volume and weight and mass are going up by the cube, you get this relationship. The surface area is directly proportional to the size squared, the size meaning some linear dimension, how wide it is, how tall it is, over the volume, which is related to that dimension cubed. But when you take a number that's squared divided by the same number that's cubed, you can cancel out two of those sizes on the top and two of those sizes on the bottom, and you'll just be left with 1 divided by size. So it turns out that the surface area to volume ratio is just equal to, is just proportional to 1 divided by the size. Now, what does this mean? This means that this ratio, think of the surface area to volume ratio as a single variable. We'll just call that x, okay? That variable on the left is inversely proportional to the size, because size is over on the right side of this, it's on the bottom. So the surface to volume ratio, the surface area to volume ratio on the left, is inversely proportional to the size. That means if you change the size twofold, you will decrease the ratio of surface area to volume twofold. If you increase the size 100-fold, you will decrease the ratio on the left 100-fold. And you see this if you actually look at the ratio. So here's that one by one cube, 1 by 1 by 1 cube. And if you unfold it and look at all 6 sides, you see it still has a volume of 1 cubic centimeter, 1 by 1 by 1. And its area of each side is 1 times 1, that's 1. But there's 6 sides of a cube, so it has an area of 6. We're not going to look at the units for a second. So its area is 6, its volume is 1. That's a ratio of 6 to 1, or 6. If we double that side length, so we're doubling the quote-unquote size, the linear size, so now it's a 2 by 2 by 2 cube. Each of the squares becomes 2 by 2, that's 4. You have 6 squares, that's 24. 24, your area, surface area of all the sides is 24, but your volume has gone up to 8. So now if you look at the surface area to volume ratio, it's now 24 to 8, or only 3 to 1. So what happened here? We doubled the size. We went from a 1 cubic centimeter, a 1 centimeter cube to a 2 centimeter cube. And the ratio went from 6 to 1 to 3 to 1. It went down twofold. So we doubled the dimensions of the cube, and we halved the ratio of area to volume. If you look at the 3 by 3 by 3, you see the surface area. I won't go through it. Each side is 3 by 3. That's 9 times 6 sides is 54. It's a cubic volume of 3 by 3 by 3, 27. So 54 divided by 27 is 2. So if you compare that to the first one, it's 3 times smaller than the original. 6 to 1 is 3 times bigger than 2 to 1. And because you increase the dimensions threefold, you decrease the ratio threefold, not the individual pieces. You have to keep track of those. So here we have a cube, a 1 centimeter cube cubed. Okay, in other words, it's 1 centimeter by 1 centimeter by 1 centimeter, and it's scaled up to a 10 centimeter by 10 centimeter by 10 centimeter cube. How much does the ratio change? The surface area to volume ratio. So we're looking for the ratio. Now you can work out each of the individual pieces, but remember, you're increasing the linear dimension tenfold, so the ratio of area to volume should go down by the same number tenfold, and therefore it's 1/10 of the original. So that's using this ratio. The one on the left is the one I just showed you. I just switched the order. And the one on the right is I literally inverted both of them. Instead of 1 over size, I made it size, and instead of surface area over area of volume ratio, I made it 1 over the ratio. You can look at it either way, whatever way is easier for you to think about. If we scale up the size tenfold, the ratio will go down tenfold. It's as simple as that. They're inversely proportional. If you want the math details, you've got a cube 1 centimeter cube, we already know it has a surface area of 6 squared centimeters. That's all the sides added up. And we know it has a volume of 1. But if we look at the big one, it has a volume of 1,000. It's 10 by 10 by 10. And the area of each side is 10 by 10 or 100. And we've got 6 of those. That's 600. So the ratio that we used to have is 6 to 1. The new ratio is 600 to 1,000, which is 0.6. So we went from a ratio of 6 to a ratio of 0.6. And all you'll notice is the new ratio is 1/10 of the old ratio. You don't have to work out all the individual pieces. You know that there's an inverse relationship between the size, the linear size, and what you do to the size, and that ratio of surface area to volume. Change one, the other will change down. If you increase one, the other will go down by the same amount, and vice versa. And that will stop here. Thank you.